Hello, everybody, and welcome to the second video for week 9. Today we're going to talk about the Legendre symbol, which is a way for computing when a number is a square modulo p. And so this is going to build on a lot of the things we did in class on Tuesday. So on Tuesday we did exercises 1 and exercises 2, exercise 1 and 2 on the worksheet. And so if you haven't looked at those yet, if you weren't in class, I encourage you to look at those for a little bit before starting this lecture. Okay, so let's get going. So what were we doing in class on Tuesday? We're answering the question, what are the squares in FP? So which numbers in FP, which elements of FP can you get by squaring another element of FP? And that's really the same as asking what are the squares mod P, which I mean, so we just list out 0, 1, 2 squared is 4, 3 squared is 9. So 0 squared, 1 squared, 2 squared, 3 squared, 16 is 4 squared, 25, and so on. And you just look at sort of what you get when you reduce all of these mod P. So now the question of what are the squares in FP is the same as sort of what numbers can you get by reducing squares of integers modulo P. Okay, so just an example, we can look at the squares in F13. And if we want to compute those, what we can do is we can just list out all the elements of F13 and then see what we get when we square each of these. So here's X is an element of F13. I'm just going to write in the bottom row the square of it. So if I do 0 squared, I get 0. If I do 1 squared, I get 1. If I do 2 squared, I get 4. 3 squared is 9. 4 squared is 16, but I'm in sort of working mod 13, so that becomes 3. 5 squared is 25. Again, sort of mod 13, that becomes 12. 6 squared is 36, and well, that's 10. So 2 times 13 is 26. So plus 10 is 36. So 36 is 10 mod 13. Good. And then if I do 7 squared, I get 49, which is 39 plus 10, so that's 3 times 13 plus 10. So if I do 7 squared, I also get 10. Actually, there's a reason for that because 7 is congruent to minus 6 mod 13. So minus 6 is 7 mod 13. But when I square minus 6, so I get 7 squared is equal to minus 6 squared, which is the same as 6 squared, because that sort of minus sign goes away when you square. And the same thing happens when I do 8 squared. 8 squared is going to give me the same thing as I got when I did 5 squared, because 8 is minus 5 in F13. So I get 12 here. You can check, I mean, 64 is 64 is 5 times 4 times 13 plus 12. Okay, and so on. So when I do 9, I get the same thing as minus 4. So I just sort of repeat. I went up these numbers and then I'm just going to repeat them back. So 10, 12, 3, 4, sorry, 9, 4. Minus 1 squared gives me 1. Okay, and so now I've sort of computed, so I've squared everything and I'm just going to write those in a nice list. So the squares are 0, 1, 3, 4. So I'm just copying down. I'm just doing increasing order. I'm just copying down everything I got on that bottom row. 9, 10, 12. And the non-squares is everything I didn't get. So that's 2, 5, 6, 7, 8, and 11. Okay. So a couple of things we talked a little bit in class, but I just want to highlight here is that I only had to go up to 6 when I was sort of making this table, because I knew everything else was going to sort of give me just negative of things up to 6. And so I was going to get the same square. And in general, you only go up to p minus 1 over 2. And moreover, if I look at sort of the non-zero squares and non-squares, I have the same number. I have 1, 2, 3, 4, 5, 6. 6 non-zero squares, 1, 2, 3, 4, 5, 6. 6 non-zero non-squares. And actually, there's always p minus 1 over 2 non-zero squares or non-squares. So exercise 1, part 2 asked you to justify the statement, and we talked a little bit about how you do this in class on Tuesday. And so the main thing is just this observation that you only have to go up to p minus 1 over 2 to see all the things, all the squares. Okay, so when we did these computations in class, I asked you to sort of compute like a table like this for p all the way up to, for all the odd primes less than or equal to 31. And then to look and sort of try and notice some patterns. So the first pattern, which was sort of in exercise 2, part 1, that a lot of people sort of worked out in class, was that sort of it seems like minus 1 is a square in FP, if and only if P is congruent to 1 mod 4. And in fact, this is so, and this is for P and odd prime. So, and this is true. Not only do you observe this for P up to 31, but this is always true. Another thing, so we're going to justify that next week, but for now, we're just sort of looking at observations from doing computations. In exercise 2, part 2, you looked at when 2 is a square in FP. And not too many people got all the way through this, but if you look back at your computations, what you'll notice is that this is true exactly when P is congruent to 1 or 7 modulo 8. So if P is 3 or 5 modulo 8, this won't be true. And then the last pattern I asked you to look at, and I don't think many people got very far in this, but I want you to look at, so what happens if I take P and Q 2 odd primes? So we want to compare when P is a square modulo Q to when Q is a square modulo P. And if you look at the data you collected, you'll notice you can sort of verify the following very interesting pattern. So if at least one of P and Q is congruent to 1 mod 4, so for example, e.g. P equals 5, Q is equal to 11. So here 5 is congruent to 1 mod 4, even though 11 is not, that's fine. So if that's the case, then actually it turns out that P is a square in FQ, or so P is a square modulo Q, if and only if Q is a square modulo P. So in a priori, there's no reason these two, and a priori, there's no reason whether P is a square modulo Q should be related to whether Q is a square modulo P. These are two completely different statements, but it turns out they are related and sort of they're equivalent. Whereas, so if both P and Q are congruent to 3 mod 4, then you do get the same kind of statement, so you just have to change it slightly. So it turns out in that case, P is a square in FQ, if only if Q is not a square in FP. So somehow you can still check sort of by swapping P and Q, you just have to sort of negate the statement. So P is a square in FQ, if only if Q is not a square in FP. That's it, both P and Q are congruent to 3 mod 4. So this would be, for example, if P is 3 and Q is 7, you'd be in this situation. Okay, so let's see these patterns just in some concrete examples, just to put them into our head. So if we look at this first pattern, the one about when is minus 1 a square, that's when the pattern we notice is a square when P is congruent to 1 mod 4. So for example, when P is 5 or P is 13, these are congruent to 1 mod 4. And like when P is 5, well, minus 1 is congruent to 4 mod 5, which is 2 squared. So that verifies that. And for F13, well, we could write them up, but in fact, we've already done that. So for in mod 13, minus 1 is 12. And we saw that 5 squared is equal to 12 mod 13. So that checks out. Okay. And so the reason sort of the reason -1 was always a square, was a square in these two cases, is somehow it's because 5 and 13, these two primes we're looking at, is congruent to 1 mod 4. Whereas you can check, it's -1 is not a square in F3, F7, or F11. So it's not a square mod 3, 7, or 11. For example, mod 3 -1 is equal to 2, but the only squares mod 3 are 0 and 1. And you can sort of look at 7 and 11 yourselves to verify that statement. Okay, so going on to the next thing, when is 2 a square? So that was supposed to be when P is congruent to 7 or to 1 or 7 mod 8. So 7 is congruent to 7 mod 8. 17 is congruent to 1 mod 8. And in F7, so 3 squared is congruent to 2 mod 7. So good, so 2 is a square. And in F17, so 6 squared is congruent to, well, that's 6 squared is 36. That's 2 times 17 plus 2. So 6 squared is congruent to 2 mod 17. So good. So 2 is a square in F7 and F17, as sort of predicted by this criterion, because 7 is congruent to 7 mod 8, and 17 is congruent to 1 mod 8. And then it's not a square in F3, F5, F11, or F13. So for example, if we look mod 13, so 3 and 11, these are congruent to 3 mod 8, and 5 and 13 is P congruent to 5 mod 8. So not 1 or 7. And if we look in our table for F13, we can just check that 2 is not a square. Indeed, here's our table. 2 doesn't appear on the bottom row. It's listed down here in the not a square list. Okay, so that checks out. Good. To give some examples of this last observation, so this observation about when you can sort of flop P and Q and sort of still be answering the same question or the negation of the question. Let's look at some examples. So 5 is a square mod 11. 5 is 4 squared mod 11. And 11 is a square mod 5, because 11 is congruent to 1 mod 5, which is 1 squared. So 11 is a square mod 5. Good, and that's as we expected, because if I take P equals 5 and Q equals 11, then P is congruent to 1 mod 4. So what this observation said was that if at least one of P or Q is congruent to 1 mod 4, so in this case, 5 is congruent to 1 mod 4, then these two are the same. Like if 5 is a square mod 11, then 11 is also a square mod 5. Okay, let's check another example. So if we look at 3 and 5, well, 3 is not a square mod 5. The only squares mod 5 are 0, 1, and 2, or 0, 1, and 4. And 5 is not a square mod 3, because 5 is congruent to 2 mod 3 is not a square. The only squares mod 3 are 0 and 1. So good, so again, these match up. So 3 is not a square mod 5, and 5 is not a square mod 3. So you get the same answer. And again, the reason we expect, based on our observation, to get the same answer is because 5 is congruent to 1 mod 4. So we're supposed to get the same answer whenever at least one of these is congruent to 1 mod 4. And then let's just check this case where they're not congruent to 1 mod 4. So if I look at 3 and 7, they're both congruent to 3 mod 4. So in this case, sort of what was my observation? Then it's supposed to sort of be the opposite. So P should be a square in FQ if and only if Q is not a square in FP. And we can check, well, 3 is not a square mod 7. So the squares mod 7 are 0, 1, 4, and 2. So 0, 1, 2, and 4 are the squares mod 7. In particular, 3 is not a square. But 7, which is congruent to 1 mod 3, is a square. And 1 is 1 squared. So 7 is a square mod 3, but 3 is not a square mod 7. But that's what we're supposed to do. It's supposed to sort of swap, sort of supposed to negate when both P and Q are congruent to 3 mod 4. Okay. So this last rule is called quadratic reciprocity. And it's very useful because somehow, I just want to point out, like, oftentimes one of these questions is easier than another, like whether P is a square mod Q or whether Q is a square mod P. So for example, if you look at this first example, it's a lot easier to check that 11 is a square mod 5 than it is to check that 5 is a square mod 11. Okay, so we sort of observe these properties, and then so here are just some examples illustrating it again. I want to now make a definition that will let us encode these properties in a useful way for making computations. And so that definition is of the Legendre symbol. So I take P to be a prime number, and then N is an integer with P not dividing N. And then I write sort of N dot 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 P. So this is the Legendre symbol of N over P. Sometimes people write just a solid line here, but I like this. I like these dots because then you don't get confused with fractions. Okay, but this Legendre symbol is defined to just be 1 if N is a square mod P, and -1 if N is not a square mod P. So it tells you whether Legendre symbol tells you whether N is a square mod P by sort of whether it's 1 or -1. But somehow encoding it this way is from 1 or -1 lets you express these patterns we observed and some other patterns in a really useful way. So that's sort of why we encode it like this. So just for example, the Legendre symbol of 18 over 5 is -1. So to justify that, I need to say that -1 is not a square mod, sorry, the 18 is not a square mod 5. But indeed, 18 is congruent to 3 mod 5, and that's not a square because the squares mod 5 are just 0, 1, and 4. Okay, so what are the nice properties of the Legendre symbol that we're going to use? So most of these follow either directly from the definition or from these patterns we observed. There's one that's new. So again, let P be an odd prime. Well, the first one is just sort of from the definition. So this says if N is congruent to M mod P, then sort of the Legendre symbol of N over P is the same as the Legendre symbol of M over P. And that's just because what is the Legendre symbol defined to be? It's about whether the number is a square mod P. And obviously that only depends on N sort of modulo P. So this is sort of just, this first property here is just encoding the fact this only depends on N modulo P. Okay, so this next property, which is extremely useful and which we haven't talked about yet, but we'll talk about next week and sort of observe and justify next week. And you could always go back in your data and look at this to sort of observe and justify it, is multiplicativity. So if I look at the product of AB, and I take the Legendre symbol of that over P, then that's equal to the product of the Legendre symbols for A and B. So somehow, if I know whether A is a square and I know whether B is a square, then I can also tell whether AB is a square. Okay, so that's a very useful one. And then the next three are sort of encoding these patterns we just observed. So the first one just says the Legendre symbol of -1 over P is 1 if P is congruent to 1 mod 4 and -1 if P is congruent to 3 mod 4. So this is encoding our condition that we observed above for when -1 is a square mod P. Similarly, the Legendre symbol of 2 over P is 1 if P is congruent to 1 or 7 mod 8 and -1 if P is congruent to 3 or 5 mod 8. So again, this just encodes what we already observed about when 2 is a square modulo P. And let me highlight sort of in both of these, I've only sort of discussed what happens when sort of P is an odd number modulo 4 and an odd number modulo 8. That's because P is sort of assumed to be an odd prime. So P is sort of never going to be an even number modulo 8 or an even number modulo 4. So you only have to look at these odd numbers. Okay, and then the last one encodes this quadratic reciprocity law. And so one sort of very succinct way to write it is to say that the Legendre symbol of P over Q times the Legendre symbol of Q over P is equal to -1 to P minus 1 times Q minus 1 over 4. This is sort of Q is another odd prime. This is a very useful way to encode it. Sort of if you just want to write down a succinct mathematical formula that expresses it. This isn't sort of so convenient if you actually want to compute Legendre symbols, but really sort of writing this equation, if you check case by case, means somebody just multiplying together sort of plus or minus 1 a bunch of times. And if you sort of check what this means sort of case by case, really what it's saying is exactly what we had before. So this says the Legendre symbol of P over Q is equal to the Legendre symbol of Q over P if one of P or Q is congruent to 1 mod 4. So this is encoding this idea that when one of those is congruent to 1 mod 4, checking whether P is a square mod Q is the same as checking whether Q is a square mod P. Then otherwise, if both P and Q are congruent to 3 mod 4, we get Legendre symbol of P over Q is the negative Legendre symbol of Q over P. Again, this is corresponding to this case where when P or Q were congruent to 3 mod 4, what we observed in the data was that it seemed like sort of the answers were opposite. So if P was a square mod Q, then Q was not a square mod P, and vice versa. Okay, so and in fact, yes, so the point of this theorem is to encode in a useful way the fact that all of those properties really hold. So all those things we observed, that you can really sort of establish and prove that those are actual sort of consistent properties that hold. So we're going to talk a lot about how you justify this theorem starting next week. But for today and sort of on Thursday, we're just going to look at how we can use the Legendre symbol and use these properties to compute interesting things. And so I want to end the lecture today by just doing an example of that. And so let's just answer the question, is 39 a square modulo 59? Okay, and to answer that question, by the definition of the Legendre symbol, I just have to sort of compute the Legendre symbol of 39 over 59. And the answer is yes if I get 1, and the answer is no if I get -1. Okay, so let's do that computation. So first I'm going to observe that 39 factors as 3 times 13. Then I'm going to use multiplicatively to spread that out as the Legendre symbol of 3 over 59 times the Legendre symbol for 13 over 59. Okay, and now I can just compute each of these separately. So let's do this first one. So Legendre symbol of 3 over 59. I should have said 59 is a prime number. Well, let me apply quadratic reciprocity. So in this case, both 3 and 59 are congruent to 3 mod 4. So I'm in the second case of quadratic reciprocity, where the Legendre symbol of 1 is sort of the flopped Legendre symbol, but with a minus sign. So I get 3 over 59 is equal to the Legendre symbol of 59 over 3, but I have to put this oops, sorry, I'm controls writing. Just put this minus sign in front of it. Okay. And then now let me use this first property. The Legendre sort of symbol only depends on n mod p. And so I can reduce 59 modulo 3, and I get just 59 modulo 3 is 2. So I get sort of 2 over 3. 2 is not a square mod 3, so this is minus 1, which is equal to 1. So to compute this Legendre symbol of 3 over 59, so first I applied quadratic reciprocity. Which flipped the symbol and introduced a minus sign. Then this symbol is much easier to compute because I could reduce 59 mod 3, and I got this just 2. And then I just it's easy to check what are the squares modulo 3, and I choose not one of them. So I got -1 here. Combined with my other minus sign, and I got a 1 here. Okay, so good. So if I plug that back in here, then I just get that I'm looking at the Legendre symbol of 13 over 59. So this part is all that's left because this just became a 1. And let me do the same thing to compute that. So I'm going to use quadratic reciprocity. And in this case, I don't get a negative sign because 13 is congruent to 1 mod 4. So again, so as long as one of the things you're flipping, one of the primes is congruent to 1 mod 4, you don't flop the sign. So here we use that 3 and 59 were both congruent to 3 mod 4. Okay, so that's why we had a sign over here, but we don't have a sign over here. Okay, then I reduce 59 mod 13, and I get 7. So 59 is 4 times 13 plus 7. And at this point, I have 2 options. I mean, I could just compute all the squares mod 13, which conveniently I've already done. So let me just look at my table. And I see 7 is not a square mod 13, it's a non-square. So I get -1. Or if I sort of didn't remember that I just computed this and sort of didn't want to compute the squares mod, 13, then I could also just use quadratic reciprocity again. And then you'd be looking at 13 over 7, which is equal to 6 over 7, which is equal to -1 over 7. And well, we know -1 is sort of by the first rule. So we know -1 is not a square mod 7 because 7 is congruent to 3 mod 4. So this is -1. Okay. So the answer when I compute all the way out, though, is that this Legendre symbol is equal to -1. And so sort of I conclude that 39 is not a square mod 59. Okay, so this took me a second because I had to explain all the steps I was doing because we're just learning this. But once you get the hang of it, sort of going through these steps goes really quick. And certainly it's a lot quicker to go through these steps than it is to just compute all the squares modulo 59 to check this. So this actually gives you sort of really nice, quick way to reduce this checking whether something's a square to a simpler problem. Okay, but we're going to play a lot more of this in class on Thursday, and I will see you there.